Okay, so yeah, I'm Mark Gifford. I'm Technical Services Manager with IES, otherwise known as Integrated Environmental Solutions. So you might know us, anyone in the audience, IES make the software platform called the Virtual Environment, or the IES VE. It's a building design tool, and it's used to do a lot of the operational energy calculations. It's a lot of Part L UK code compliance software. Yeah, so I've been with IES about 13, 14 years, traditionally from a M&E design consultancy background. I've used the IES software extensively for code compliance, lead energy modeling, and then more recently I've moved into sort of data analytics, looking at monitoring-based commissioning. So today we'll be looking at BMS data, smart meter and utility platforms and things. The topic I've been given is monitoring and identifying the need for retro-engineering. So it's obviously quite a vague, wide-ranging topic. So just to sort of jump in and give you our sort of take on it. So just a quick intro of what I'll be looking at. So identifying the need, we'll look at that in a very sort of general context, identifying the need in a few sort of simple life examples. We'll then look at sort of retro engineering within buildings directly. We'll look at some standard workflows and methods that typical consultants like myself and Cavendish might use. Take a look at the sort of focus on technology, some of the technology, the platform, some of the tools that can help, and then we'll look at a sort of retro engineering example and a sort of case study that we've done. So yeah, without further ado, a quick intro on IES. So we're a global company based out of Glasgow in Scotland. We've been around now for maybe 25 years. We're the UK market leader. We also have a global presence. We're established globally, so we have about over 160 employees now. Headquartered in Glasgow, which is where I'm from. We also have regional offices in Dublin, a presence in the States, Atlanta, India, and we also have some representatives in other world locations, including Singapore, Middle East, Australia. You probably best know us, anyone in the audience who uses the IES design software. So we're best known for the IES VE, the software suite. It's like a building analysis platform. But we also offer energy services consulting as well, both using the IES software suite and also on the energy optimization, energy consultancy side. Okay, so retro engineering, I thought it was really important, if you like, to maybe take a step back and just look at identifying the need. So we've had a play on this, but when it's obvious, you've got a flat tire. So how do you tell you've got a flat tire? You hear a noise, you're feeling the vibrations. Clearly there's a problem, and it's obvious that something's actually wrong. Another example that's happened to me is your kind of 5-year-old comes to you and says, Daddy, I've kind of broken my toy, and you maybe have to say, well, I'm a building services consultant. I'm not a kind of surgeon, but again, the need is there. It's an obvious sort of solution is needed. A quick look at an X-ray. You've broken your arm. Again, it's an obvious one. So you go to the doctor, and ultimately you get your pulse taken, you get the health check. These are all real-world obvious examples. But then we come to the sort of building sector, and this is one Zaha Hadid architects built this. This is the Riverside Museum, based on the banks of the Clyde in Glasgow. Probably opened about 2010, so it's a new state-of-the-art building. My building's beautiful. Yep. It even has a badge, so maybe it has a BREEAM certification. It's BREEAM Excellent, it's BREEAM Outstanding. It could be LEED, it could be WELL. From my experience, the more badges, the more awards the building's won, then probably the worse it is from an operational energy perspective. So we'll maybe take a look at that today and understand what's going on under the bonnet. So I've sort of broken this into two themes, as the sort of reactive engineering side, or reactive retro engineering, and then we'll look at sort of proactive as well. So how do you know you have a problem? You've got your sort of flagship building just handed over. I think the sort of year 1, year 2 handover is a bit like the sort of honeymoon period where everyone's excited. We've got the new building, we've got the keys. Isn't it great to be here? So how do you actually start to know you've got a problem? So typically, you're going to get a high energy bill. Might be the first indicator that something's wrong, and the CFO, energy manager, he's in a state of shock. Is this how much the building costs? You might be looking over 3-4 year cycle, and you start to see you've got a really high energy bill, high maintenance budgets coming into play. Again, another main theme of you have a problem. And I think finally the age-old thermal discomfort or thermal comfort. Typical office in London, somebody's too hot, somebody's too cold, somebody went to the gym at lunchtime and worked themselves up, so it's very difficult. But typically that's where your HVAC systems could be performing a bit better. So these are all indicators that you have a problem, and I call that reactive engineering. But what if benchmarking? Yeah, one slide I forgot I had. So in benchmarking, this can be legal in general, or obviously here. So with an organisation who has multiple buildings and they have access to that energy information, it can be very easy for these kind of guys to say, well, I've plotted it on a scatter plot, and this building here is an outlier. It's using more energy than it should. That's fine because you're comparing it to known information. This guy on the right-hand side, he's a bit left out because he only owns one building, so he doesn't have access to the club. He doesn't know what a typical office in London might use. So how does he kind of look at, is his building running right? Is it not? He doesn't know. So yeah, for that single owner operator, it's not that easy. Maybe touch on it later, but maybe a sort of open available data. We need to look at opening data up, publishing more information about performance. And even then, it doesn't take away the unique situation where you have a state-of-the-art museum, you have some new sports arenas, you have a primary school which could be a low zero carbon design. So it could have a heat pump, it could have CHP, it could have biomass. All this is new territory, so your benchmarks don't often reflect the new design concepts. So it brings us to what I'd call proactive engineering. So from an engineering perspective, like myself, I think engineers, we want to look below the surface. So the tip of the iceberg is a bit of the building that Joe Blogg sees. He's the office worker. He's happy in the building itself. But the engineers, we see the bit below the waterline. We want to look at the M&E services. We look at the switchgear, look at the metering. We want to understand what's actually happening below the surface. And I think that's really the key theme for me. We can look at this more. But before you can start identifying if you have a problem, you need to look at some form of proactive monitoring exercise, really, just to take the pulse. And yeah, that's what we're looking at now. So data in buildings, it comes in all sorts of shapes and forms. Maybe taking a look at water to start with. So we have water meters. What we now have is like half-hourly water meters, where the water meter is giving you half-hourly information. That's also the same with electricity and gas. So these technologies where your main utility meters are giving you info, that's known as automatic meter reading. So AMR is a big concept, a big tool that can help. At the top, we've also got the BMS. That gives us information like temperature information, quality information, air quality. We might have a weather station in the building that can give us climate information. Some of the lighting systems are becoming much more modern, the likes of Dalibus. Some of these things can tap into the BMS, and you can wire your submetering and your lighting system through the BMS as well. So there's lots of different systems that give us data, and it's pretty much at the moment a very untapped resource for buildings. And what we're saying is if you can harness this information, it can become really valuable. So we're looking here over time. You can use more data to create a clearer picture of the building. So the concept is a bit less data on the left. The visual representation of that would be over here. And as you get more information, the picture becomes clearer, more concise as you move through. So more data allows you to capture and manage the building more effectively. And to do this, you have to look at your data collection. It's not enough to be doing monthly bills anymore, monthly meter readings. You want to get into the sort of half-hourly resolution data. And for that, you need to have a well-managed, well-organized process of how you get the data. That's going to throw up things like gaps. The gaps will appear, and that means you can start to fix where do you have the gaps, where do you not, how do you fix it all. And all this just leads to ultimately better analysis. So what we have to do, back to the doctor at the start, we have to take the pulse of the building before you actually can say, well, is the heartbeat regular, irregular, is the building working well, is it not? Okay, so utility metering. This is an example of just a main meter. You can see the AMR badge, and the meter has a barcode. It's a smart meter, and it communicates half-hourly information. So AMR, a huge resource for any kind of energy manager out there. You want to be asking how do I get access to my AMR, my half-hourly data. Typically, you're going to get it on electricity, gas, and probably water. In addition, submetering can also give you that. If the submeters are actually wired back to the BMS, what we find a lot of the time is the submeters are installed in the building, but they've never actually been wired back to the BMS. So unless you're going to walk into that plant room once a day, once every half hour, and take a manual reading, and then type it into a spreadsheet, you're not going to have that information. It's a big area that gets cut at construction handover, where a contractor might put the submetering in, but he never actually wires it back to the BMS head end. So you definitely want to get access to your submetering. I think finally the BMS, the building management system. Typically, this is some sort of maybe 1980s, 1990s retro graphics, but there is information in there that can be useful. Again, it's a case of understanding how you can access that information more effectively. So with the BMS, I thought it's maybe useful just to give you another real-life example in terms of retro engineering. So I don't know who's in the audience, but if you're running buildings, you could have a building that's 20, 30 years old. So typically you might find that some of your control system, the mobile phone equivalent to that would be this really old sort of handset. And you should find as you've moved through the decades, through 2000 and into 2010, you can see that mobile phones have evolved, but so too have building management systems. So I'm not giving you an answer to this. Retro engineering, you need to consider, do you have this BMS? Do you have this BMS? Can that BMS be upgraded? Or can it give you the information you need? It's not a perfect science. Just be aware of the fact that there's, that's out here. And I think as well, this is an interesting one about data. So the price of data, there's an exponential y-axis. So you can see that over the decades, the price of data has got exponentially cheaper. So in 2010 even, you can see you're paying about 10 cents per gigabyte, whereas through into 2015, you're down to less than 1 cent per gigabyte now. So data storage has become a lot cheaper. And if you think about these systems that were maybe designed in the 80s, 90s, they weren't ever designed with data in mind. What you do find is the more modern BMS architecture has been designed maybe a bit more with data in mind. So you can you get into that data. A couple more challenges, or a few challenges. When you start to get into data from different systems, you've got different formats. Some are maybe in a database, some are in a CSV, comma-separated value file. So the different formats, different places to get the data. The frequency of trending, we talked about half-hourly data, but your standard BMS system might give you like 15-minute interval data. So then you need to consider how can you put those two together, how you can compare 15-minute data alongside 30-minute data. How do you fill the gaps in your data? how do you take away outliers, how do we plug the holes, so data repair becomes a key theme. I think the big one really is obviously network access, security, the cyber risks of getting data from a building. That's a huge area as well. So if we can track information over time, this is what we can get. So this shows you a sort of heat map, and it shows us half-hourly electrical use over a 6-year period. Down at the bottom, we have 2013. The red indicates a higher energy use, and as we then move through the years, you can see that we were actively tracking that building over time, and then we can see last year in 2017, 2016 as well, we can sort of visually see the seismic shift from a high energy using building to a sort of medium intensity use. But again, you're not going to get into this pattern recognition if you don't have the data. So you need to get access to the data, address some of the previous challenges, and then when you've addressed those, you get your data coming. Then you can start to get into the analytics, the visualization side. Just a bit more detail. This is maybe how it looks for my guys, a bit more advanced. We're looking at 2 or 3 BMS points, and we can identify issues with this, maybe a heating valve running when it shouldn't be, but that's more advanced analytics. Okay, so case study, actually on the same building that we looked at. So Riverside Museum, the Museum of Transport up in Glasgow. As I said, it's Zaha Hadid. It's the big sort of fancy design. So we got access to the submetering data for this building. So it's maybe 20, 30 submeters, and we've been logging information for maybe a couple of years now. So 2 years for all the submeters. I think what's interesting is the top 3 submeters in this building combined use more than the rest of the submeters in total. So just to explain that again, the first 3 submeters, when you add up them, they actually take up more energy flow than all the remaining submeters. So you can see some of the meters at the bottom where we have maybe 5, 10 submeters. They don't really register any energy flow across them. If they do, it's very minimal. So what you've actually got there is almost like a misuse of the meter. The meter's gone into a place where it's not useful to actually monitor anything. Whereas in the top circuit here, mechanical control panel 1, then you can see that's a huge component of energy use, but we don't have any more visibility on where that's going. So, an example of retro-engineering could be take some of these 3, 4 submeters and maybe recycle them back up to top of the line and try and break up that load a bit more. So there's definite potential for data to really enhance the submetering strategy within a building. Just another view, when we look at some data, on the left-hand side is the main incomer, and we can then look at the submeter information. So when we look at the balance between the right-hand side and the left-hand side, we can work out is there any unmetered component, and quite often, unmetered could be a big component in the building, 50% unmetered if your submetering strategy is not good. If your submetering strategy is good, then you should have a relatively small component of unmetered use. Again, we can see that the MCP panel takes the biggest energy flow. For some of this stuff down here, it's not really much use. I think these ones down here are all doing the exhibition lighting. So within the museum, what we found is the existing energy team in the building, they were scurrying around, let's replace the lighting, let's put in LED lights on the exhibits. You're never going to save any energy when you do that, when your big users are heavy energy hungry. So we would say, like, pick mechanical panel 1, find the plant associated with mechanical panel 1, and obviously target your energy saving interventions on that area. Otherwise, you're just wasting your time. So retro engineering done right, you can really sort of target where you need to spend the money and your effort. Again, just another view. So it's a pie chart. We can see over 50-60% of this building is gone on plant. So by looking at exhibition, you're never going to save your big hit. Again, just another few examples. Out of hours heating, we can look at different type of visualization. Same version, a different version of the same thing. We can see here the 8 a.m. until sort of 6 p.m. Out with that time frame, something's wrong, something's happening that shouldn't be happening. So we use data, we use visualization techniques to really, tune the building and iron it out. So I think just in summary on this site, this is the work we've been involved with over the last year or two. So we've used the data and we found big issues with the CO2 set points, and these were holding the sort of fresh air dampers open. There was also issues with the heating valve on the air handling units. Again, lack of thorough commissioning. So just by working with the client and working with the client's maintenance team, we could offer active advice on how to just tune the building more effectively. Similar, the chilled water pumps, there's some issues around just the operation of these, different bits and pieces, boiler flow temps, air handling unit, supply pressures. But listen, all of that put together led us to, within 1 year, we achieved 16% energy savings on this site, and that's based on 2016 versus 2017. As I said at the start, this building opened in 2010, so in some ways the building probably ran in the 2016 mode for the first 6-7 years, where after our guys got involved, we took it down. The argument is that those savings should have really been in there from day one. As I said, it's a flagship project, so that the concept is never assume that your building isn't suitable for retro engineering. Just because it's a brand new day one handover doesn't mean that it's not the time to get involved with any of this retro engineering. On the gas side, the savings were better, so 16% savings electrically in that first year. We got up to 23% on the gas. Combined, you get a near sort of 40% energy savings. So it's definitely an example of retro engineering through sort of better data. It's important to say with this site that we didn't actually spend any money other than the consultancy side sort of fee. So there's no capex going on additional hardware. Those savings were really achieved through just looking at the data, the sort of retro engineering approach to it. I think that's us now. Yeah. Anyway, just to the skip over. So yeah, thanks for your time.